Okay, this is question 2004 B, meaning it was a B exam that year. They used to have an A and a B, and the B was for kids that were sick on the first day. Um, so answer the following questions related to hydrocarbons. The first thing I need to talk about is the fact that this is a term that you should probably remember from your unit on writing chemical reactions, is that when something is a hydrocarbon, that name is pretty self-explanatory. It's an organic compound that's made up of only carbon and hydrogen. That's it. There's no oxygen, no nitrogen, nothing else. It's a hydro for hydrogen and carbon. And so the first question, this is an empirical formula problem, 85.7 grams of carbon. And if it's 85.7 grams carbon, it has to be 14.3 grams of hydrogen. By the way, I skipped something hugely important there. The reason that the formula of a chemical compound is not dependent on the amount of matter present. It's an intensive property. So if you have a little cup of water, the formula is H2O. If you have a swimming pool full of water, the formula is still H2O. The chemical formula does not change based on the sample size. And so what happens is when you're doing an empirical formula thing, the reason why you can go from percent to grams is it's independent of sample size. And so you can assume any size sample you want. And so the best size sample to assume in a percent problem, because it means per 100, is 100. So now, and so the 14.3 comes from, if it's 85.7% carbon, then it has to be 14.3% hydrogen, because the 2% have to add up to 100. Well, this is 12.01 grams, goes down to cancel in a mole, because the mole is the most important concept in all of chemistry. When you do that on a calculator and round to 3 sig figs, you get 7.14 moles of carbon. And then when you do the same thing for hydrogen, 1.008 grams of hydrogen and 1 mole of hydrogen. This has 3 sig figs, this has 4, and the ones are implied. This ends up being 14.2 moles of hydrogen. I wasn't your teacher last year, but I would tell the kids this is called the silly looking formula. But you can do the silly looking formula right now if you want. Or you can do it over here, but what you do when you have a silly looking formula is the mole ratio, because for instance, when you have water, what this really means is there's a 2-to-1 mole ratio. Well, this has a 7.14 to 14.2 mole ratio, but you can't have fractions in formulas. So 7.14 divided by itself is 1, and 14.2 divided by 7.14 actually comes out to be 1.989, but for all intensive purposes, 2. And so this is the empirical formula. And then remember, the empirical formula is not, it may or may not be the real formula. The empirical formula, the definition of that is the simplest whole number ratio between the elements. It could be C2H4, C10H20, but the simplest whole number ratio is 1 to 2. All right, so then I think that's all that's on this page. Let me just scroll down to be sure. Okay, so the next question is, the density of the hydrocarbon is this, calculate the molar mass. Again, here is the equation. Molar mass of a gas is Mr. T conquers over pervs. I think I explained that on our first problem. But again, this is the huge in gas laws. This is probably the most important formula, perv nerd. But N is the number of moles, and the way that you calculate the number of moles is mass divided by molar mass. You can actually see that back here, that when we have mass and we want to convert to moles, we end up dividing by molar mass. And then if you take cross products, I'll switch colors, putting a 1 here. You end up with Mr. T, like from the A team, equals PV molar mass. And if you're solving for molar mass, you get Mr. T conquers over pervs. But this is crazy because, let me grab an eraser and get rid of all this. That was just kind of a sidebar. The other thing is, one of the very first things we learned in chapter 2 was the fact that density, because you're talking about density here, is mass over volume. And so if you come over here, switching colors, mass over volume, I can sub density. It's also dRT over P. D, because M over V is density. And so if you go up here, the density is 2.0 grams per liter. R, now this is going to be different than if you look at the scoring guidelines, but I'm going to use our formula sheet, our new formula sheet, which is 0.08206. In 2004, the value of R on the formula sheet was 0.0821. And then this is an atmosphere times a liter over mole K. Not the best writing, sorry there. The temperature is 50 degrees Celsius. Well, 273 plus 50 is 323 K. And so that's upstairs, so 323 K. If it bugs you that there's nothing down here, put a 1. And then P has to go downstairs, and it's 1 over 0.948 atmospheres. Sorry, I kind of jammed myself on room here. But what happens is liters on the top, liters on the bottom, atmospheres, atmospheres, K, K. The only thing that doesn't cancel is grams on the top and moles on the bottom, which is awesome because we're solving for the molar mass of the gas. And when you do 2.0, which has 2 sig figs, times 0.0826, which has 4, 3, 3, we only get 2. And so the answer is 56 grams per mole. That's the molar mass of the gas. And then when you come down here, what is the molecular formula? Well, one of the things, this is really hard for my students when I teach this the first time, but the empirical formula times some constant, which I'll call X, is the molecular formula. And so what happens is the first thing you have to do is you have to figure out what X is. And the way that you do that is, let's say we're solving for X. It would be the molar, sorry, let's use the formula, the molar mass of the real formula divided by the molar mass of the empirical formula, which is the reduced formula. And so the interesting thing that happens here is we just figured out in I that the real formula was, or the molar mass of the real formula was 56 grams per mole. And if you go up to the empirical formula, well, on the first page, the empirical formula was CH2. Now this has to be a whole number, so I'm going to play fast and loose, but this is approximately 12, and this is approximately 1. And so this is approximately 14 grams per mole. Notice I'm putting approximately. If you were doing sig fig rules, it would be 12.01 plus 2 times 1.008. This has 2 decimal places. This has 3. Probably should have 14.03 here, but everything in formulas has to be whole numbers. And so when you do 56 divided by approximately 14, you end up with 4. Meaning that the real molecule is actually 4 times heavier than the empirical formula. And so to finish this problem, I have to extend the page. You're going to take the empirical formula, which is CH2, and you're going to distribute a 4 through, and so it's C4H8. Which is still a 1 to 2 ratio, like CH2 is a 1 to 2 ratio, but the empirical formula is the reduced formula, and the molecular formula is the real formula. All right, so now flipping to the back. Oh, I love this problem. Love, love, love this problem, although it's very difficult for me to get organized. Two flasks are connected by a stopcock as shown below. The 5-liter flask contains CH4, which is methane. That's what comes out of the gas jets, at a pressure of 3 atmospheres. And the other flask contains C2H6, which is ethane. And that's 1 liter and a pressure of 0.55, and calculate the total pressure of the system after the stopcock is open. Assume that the temperature remains constant. The thing that's crazy here is that the total pressure is going to be equal to the sum of the individual pressures. That's what I just said Graham's law of diffusion. It's not, Dalton's law of partial pressure says that the total pressure is equal to the sum of the individual pressures. So what you do here is you pretend that this gas isn't here, and you work it like this was just nothing, a vacuum, and then you pretend that this gas isn't here, and then you add them together. And so because the temperature is not changing, the P1 V1 over T1, which is not on your formula sheet, because the temperature is constant, you can cancel these. And so what we're really looking for is the new pressure after the stopcock is open, and it's kind of fun. So first of all, I'm going to do that the pressure of the CH4, this is going to be second conditions, is the pressure in the beginning times the volume in the beginning divided by the volume after you open it. And I'm going to work down because I have to do 2 parts here. And so what happens is the pressure starts out being 3 atmospheres, but the volume starts out being 5 liters. And then, interestingly enough, when you open the stopcock, the volume changes from 5 liters to 6 liters. We pretend that this is not here and this was empty. And so what happens is, and if you have number sense, this makes sense. The pressure, when you open this, because remember, pressure is caused by the collisions with the walls of the container. And it just makes sense that if you have a bigger volume, it can go further before it collides with the side. And so what happens is you have 5/6 of the original pressure. So 3 times 5 divided by 6. Everything has 2 sig figs, and that ends up being 2.5 atmospheres. Now the pressure of the C2H6 is also P1 V1 over V2. But in this case, I got to grab the eraser because I covered up my mess. So what happens is the original pressure of this guy is 0.55 atmospheres. The volume before you open the stopcock is 1 liter. And the volume after you open the stopcock is 6 liters. And what happens is, probably should show you these cancel. When you multiply, you count sig figs 2, 2, 2. And when I do this on my calculator, I get 0.092 atmospheres. And so now going up here, back to this first idea, is the total pressure is the sum of the individual pressures. And so the new pressure is going to be 2.5 atmospheres plus 0.092 atmospheres. If you do that on a calculator, you get something like 2.5092 atmospheres, but keeping in mind that when you add, you count decimal places. So this is good to the 10th, this is good to the 1000th. The answer is only good to the 10th. So the best answer is, sorry, this would be 2.92, because this is, so sorry, I did that fast. 2.5 plus 0.092, you could see 295. And then you only get 1/10, so 2.6 atmospheres is the best answer to that problem. And then This next one is what I think is the hardest problem on the whole set, because they gave you the density. I'm just going to write down what they gave you here. The density is 0.703 grams per milliliter. And then they gave you the volume, which is 2.55 milliliters. And guys, I'm just to the point where, you know, I can see units. If I do grams per milliliter times milliliter, I'm going to be in grams. And then, and this is octane, because they gave you the density of the octane. And so now we're in grams. And then the most important concept in all of chemistry is the mole. And so I know when I do C8, H18, the molar mass is going to be 8 times 12.01 plus 18 times 1.008. And when I do that, I end up with 114.22 grams per mole. This has 2 decimal places, this has 3. And so because grams is on the top, the 114.22 grams is equal to 1 mole of octane, so CH818. Because this is a Stoich problem. And why do I know it's a Stoich problem? Because you got information about octane, the density of octane and the volume of octane. And they ask about the total moles of gaseous product. Now, you can see on the balanced equation that what's in front of the octane is 2 moles of octane actually makes 34 moles of gaseous product. Where does that 34 come from? This is a G, this is a G, 16 moles and 18 moles is 14, carry the 1, 34 moles. And guys, this is how the modern combustion engine works, in that 2 moles of liquid octane makes 34 moles of gaseous product, and that 34 moles of gas takes up a lot more space than 2 moles of a liquid, and the oxygen's being sucked in from the air, so it's not there. And that, when this happens, these 34 moles of gas causes this explosion, which pushes the piston up in the engine, which is what makes it go. But anyhow, this has 3, this has 3, this has 5. These are counting numbers, and so the answer ends up being 26.7 moles of gaseous product. Now, the other way to do this problem is to do this so that you can see that it's a mass mole problem, is density. Oops, sorry. Let me grab a different color because it's a different way to do it. Density is, sorry, I lied. Mass is density times volume. And so you could do the 0.703 grams per milliliter times 255 milliliters. Don't round. This is an intermediate. On my calculator, 0.703 times 255. This ends up being 179.265 grams. And so if you go up here, this is 179.265. And kids ask me every year. And then the question is, how many moles? This ends up being a mass mole problem. Kids ask me, why'd you keep 6 figs here? Because the final answer is calculate the total number of gaseous product formed. If you round this to 179, you're going to introduce rounding error before the end. So keep them all, and then there's the molar mass. So instead of this, you would put 179.265 grams here, and then grams goes in the bottom. There's a couple ways to do it. All right, that's it.